Good morning, calculus.
Hey, good morning.
Okay. Let's see, let's go get something. Let's see, did I put this in calculus? Well, we don't need that. All right, sharing the screen. Let's do this. So you may have noticed on the syllabus that today is reserved for a chance to kind of play around with GeoGebra a bit. So I want to give you essentially two things. I want you to be able to play with GeoGebra, but I also want you to, I don't know, grow in your, that's kind of my more important purpose for today is that you would grow in kind of your conceptual understanding of vectors. So let's see if we can do this. So I want to see if you can do this mathematically. And then I want to see if you can do this on GeoGebra and kind of sort of prove the truth of what you just built. So let's see, let's do two things. Let's say we got a vector, we'll call it V. Let's see, do I want to do it this way? Nah. So let's say vector V is based on, we're going to call it sort of from A to B. And then over here, I'm going to tell you what the coordinates of these points are, just making this up, as you probably can tell. So can you write vector V? And then secondly, let's make another vector U, which will have go from C to D, and I'll make up a couple of points for C and D. Let's go 6. So what I would like you to do is see if you can tell me the answer to, I don't know, this simple question. Let's see. Now let's start with this. So first of all, can you do that entirely mathematically? Can you create the vector V and the vector U, and then can you add them together? And then what I'd like you to do is, if you haven't already done it, get on your computer, which you're obviously on, and open up Desmos 3D, I'm sorry, GeoGebra 3D. There is a 2D version, you don't want that. So all you gotta do is Google search, and you might want to favorite that if you haven't already done it. And see if you can kind of, I don't know, visualize all this. Can you actually make all that happen? And also I'm interested that you see, if you didn't see it yesterday, kind of how, because there's sort of another, there's all kinds of ways to label these. And so I just want to play around with that a little bit more, just to make sure you have a really good sense of it, the difference between an ordered pair and a vector. And the different ways those are sometimes explained. And it also just felt like it took a while to wash over me kind of the importance of throwing that little vector symbol over the top of it. And again, that's really because you're trying to distinguish between that and an ordered pair. A vector takes 2 points. It takes 2 ordered pairs to make a vector, because it's got to start somewhere and it's got to go somewhere. And it's got to have a head, it's got to have a tail. Tail's where it comes from, head's where it's going. And so, when you list a vector, it doesn't have 2 points. It just has, well, it looks like 1 ordered pair. And so, what does that mean? And you need that to just make intuitive sense to you. So I'm really kind of looking at today as just a chance to kind of soak on this before we go use it for something, because we're about to take dot products and cross products next week, and they're really cool, but you got to speak the language of vectors naturally if they're going to sink in. So between that and learning a little bit about GeoGebra, that's what I want to accomplish today. So what we learned yesterday was that if I'm going from A to B, and you may also notice I never used this word before, but really this is also the concept of array. Remember, there's segments which actually go from a point to a point, and then there's rays which go from a point through a point, and then there's lines which go through 2 points in both directions. So really what we're talking about is kind of a ray, except for rays go forever and vectors actually stop, because the length of the vector is characteristic or represents some quantity. And I'll give you an applied example of that today, which is kind of cool. So what we learned yesterday is that I need to go B minus A in order to get this to function correctly, since it goes from A to B. So if I go B minus A, I go 3 minus a -1, that's 4. I go -2 minus 3, that's a -5. I go 6 minus a -4, that's 10. And so what I'm interested in is, and I hope I gave you enough time to get that ahead of me. What should bother you a little bit is just like, what does that mean now? What's going on? Because again, it kind of looks like an ordered pair, and it is an ordered pair. Like if you go graph it on Desmos, you're going to graph the point for -5, 10. But as I said before, it takes 2 points to make a vector, a start and an end, the beginning and where it terminates, the head and the tail. Well, in this case, it's kind of assumed or important to know that the tail of this thing is at 0, 0, 0 now. And that's because vectors can be anywhere. Does that make sense? So if I said draw that vector, the tail does not actually have to be at 0, 0, 0. It could actually be anywhere. And so, the truth of this is actually, you see the difference? So from A to B, it's actually been chosen, like you're putting it in there. And so you're saying it's going to start at A and it's going to end at B, and that's exactly where that thing is. But ultimately, when you're given the vector, if I sort of didn't give you A, B, if we just kind of got rid of that and said none of this existed, and I just said, hey, there's vector V, the idea is that can actually be anywhere. I can put that any place that I want. So it is an ordered pair in a sense, but the tail can be anywhere. So hopefully you say, all right, well, okay, I got the pattern here. I knew this from yesterday. So again, I'm going to go D minus C, -2 minus 4 is -6. 5 minus a -2 is 7. 6 minus 8 is -2. So now I have these two vectors. Let me show you something else. Like you'll see this in GeoGebra, and also just different teachers will teach this differently. Another way this is written is, well, this. So you've seen this in my open math now, I imagine, but also you perhaps have seen this. This is, and I've only said this out loud, but I haven't written it that way very much. Vector u is actually 6i plus 7j minus 2k, I, j, k, effectively x, y, z. And again, it's a little annoying. And actually, I ask you guys just to think out loud, why don't they just say -6x plus 7y minus 2z? Why not just do that? What do you think? You have any thoughts on that?
Is there an answer to that?
Yeah, I think there is, but actually, I don't know what it is definitively, but I do have an opinion. I do have a guess, and I'll give it to you for extra credit to go find it for sure. But anybody have any thoughts?
In matrices, we call them like IJ. That'll be the coordinates of a number.
That's right, and it is just x's and y's, right? In 261. So why not just call it the XY element? Like, wouldn't that be simpler? We already know X, Y, Z. And so, why not? Any thoughts on that?
Well, that would look like an equation, right?
That's my thought, Ben, because now it looks like an equation of a plane. We're going to play with that a little bit today, but it looks like, because again, X, when you see X, it just means X is anything. In other words, you don't say X is 2, you say X is 2 and 3 and 6 and 5, and like X can be anything. When you see X, it's automatically assumed that X can be any number you want it to be, as opposed to a particular number. So that's my thought too. It might be confused for an equation. So I get that, but now when I see IJK, I have to memorize what order it is. At least it's alphabetical. I mean, thank you, mathematicians, for that. But notice there's actually plus signs between them. It's not like commas. And so anyway, if you want to look that up and see if Ben's conjecture and mine are correct on that, feel free. So that's another way to write that. And so for that reason, and maybe you can see here why that's the case, because again, this isn't hard, but then we'd say, okay, if we're going to use that lingo, then our V vector would actually be 4i minus 5j plus 10k. And so therefore, if I decided I wanted to add these things together, then it's kind of a, what that does is help you see, oh, I got to add like terms. If I have 4 i's and I have -6 i's, then I have -2 i's. And if I have -5 j's and 7 j's, I have 2 j's. If I have 10 k's and -2 k's, I have 8 k's. And so there's vector u plus v. U plus v added together. So that's our answer. Just as a side note, because this is what happens in GeoGebra, maybe you noticed this, but they actually write it like this. They actually write the vector like this. Here's the u vector, and they write it vertically. And here's the v vector vertically for -5 and 10. And then, of course, if you decided you were going to add them together, then you would say, oh, okay, great. That's -2, 2, and 8. So, kind of same answer. There's some advantages to that. And so there's just a lot of different ways that it's written. So notice when it's vertical like that, in a sense, you'll see essentially like a giant parenthesis around it. Notice the one cool thing about that is you can't mistake it for an ordered pair because it's vertical. Whereas back here with you, if I drew an ordered pair in there like this, then you would think it was an ordered pair. And so it's kind of important to have some different symbol. And so I think overall, that's kind of why this can be confusing, because there's all these different symbols for it. But the important thing is you see it's very distinct from an ordered pair, and yet it isn't. Like, it is an ordered pair. So it's like if I wanted to graph this final vector here, let's go ahead and try to graph this. Since this is our answer, let's make a graph of that. So again, you can sketch this, and I think you should practice being able to do this because it's not super hard. So again, you got to label these, and you can label them any way you want to, but you definitely need to label them in 3D. And so I'm going to go -2 in the X direction. So there's -2 in the X direction. Then I'm going to go 2 in the positive Y direction. There's +2 in the Y direction. And then I'm going to go 8 in the Z direction. 2, 3, 5, 6. Someone didn't plan ahead very good. That'll fit. 6, 7, and 8. And so notice, where did I start? I started at 0, 0. Why? Because I'm lazy. Like, why would I want to start some other point? Like, I already know where 0, 0, 0 is. Does that make sense? And since the vector can be any place, then let's put it where it's easy. So if I have not blown it, I'm saying this is U plus V. The question is now, can you go verify that? And again, as I said yesterday, does it make sense if I take away those little green dots that I made where you watched me count it kind of parallel to the axis and so forth? You can kind of tell where that is, but if I erase those, you have no idea where that purple vector is pointing. It makes no sense whatsoever. So the question is, if you haven't already done so, you probably wrote this down on paper already, but let's go see if we can do this in GeoGebra. Can we get GeoGebra to sort of check our answer if this is a test question? So I'm about to lose my screen. No, I'm not. I'm not going to lose my screen. I think I'm going to do this in I'm going to do this on my computer today because the ability to type, if I type, it's a little easier. Now, there's more than one way you can do this. I could just say, well, I know how to subtract, so I think I'll just do vector V right now. Or I could do vector A and vector B. I'm sorry, point A, B, and then actually make the vector from A to B. I could do that too, either one. Maybe I'll do both for the fun of it. So as I showed you yesterday, so I can literally just make these order pairs, -1, 3, -4. Hopefully you're ahead of me here because I'm not doing this to demonstrate for you. I really just want you to have time to try to do this yourself. So there's my point A, cool. Here's my point B, 3, -2, 6. And I don't know if we'll go here today, but see how there's a calculator up here? which is like you just typing. It's kind of like you're typing commands, but I can go to this, and there's actually, and I'm actually not very good at this yet, but there's all kinds of stuff you can do. Like, see how it says point right there? I could just click that and then type. And so if I click more, let's see, notice right here is vector. What I've noticed though, when I go in here, because again, I kind of want us all to teach ourselves this a little bit. You'd think if I click there, it's like I click there and I don't really understand what it just did. It says select a starting point. I think it's wanting me to go over to the screen and like click, you know what I'm saying? I'm going to try that. So I think I'm clicking A, but notice I can't really tell. And notice that cursor isn't a lot of help because I can't really tell like where it even is. So it's like, I'd like to just type my point, but I think I can click A and then click B. Okay, so I just figured out how to do that. That's awesome. So let's see if I go back to my screen. Oh, look what it just did. So you can actually just type that. I showed you that yesterday. Vector is a command. You can just type it, like start typing the word vector. Notice I didn't pick U, unfortunately. I called that V. So now I'm in trouble, right? Because that's supposed to be vector V. So can I just change it? Again, I don't know the answer to this. I'm hoping the answer is yes. Oh, good, I can. So first of all, would you agree that verifies that I didn't get the vector wrong? And notice it also listed it vertically, like I mentioned. So you should just see that as, oh yeah, that's cool. And I kind of like that because it makes it easy to add because you can write two of them next to each other. I don't have to come up with some, less than and greater than signs. I can just still use a parenthesis to write it. And so I kind of like that symbol actually. Well, for the other one, let's just go do it. In other words, for the other one, I'm just going to start typing. I'm going to say U equals capital V. I can't remember if I have to capitalize that. Notice I hit vec and it's like popping up the commands. So vector, do I want to type and stare at this carefully? Notice I have two options. I can just type a point, or I can say start point and end point. So that's kind of interesting. So let's see, I'm just going to click a point. So what's my point? Well, we already did the subtraction and it was -6, 7, -2. Again, I think I'm doing this right. -6, 7, -2. And notice again, like point, what do you mean a point? You can't have a vector with one point. Well, notice it says, doesn't like it. What's wrong? Well, the point it wanted apparently is like needs to already be named. In other words, I need to say A. You see what I'm saying? I can't do this. I thought I'd just be able to type that and it would kind of be okay. Well, this is kind of what today is about. It's like, how do I get this to work? So it wanted just point A. So it's almost like I'd have to go in and make a point called -6, 7, -2, and then I could say vector of that, and then it would do it. So I guess I'll do that because our goal today is just to kind of play around. So okay, fine. I'm going to call C the point. I hate to do that because I already called C something else. I think I'm just going to stick with what I had before. I'm not going to get fancy. I'm going to go ahead and just type it in kind of the same as we did the first one. So I've got point C and I've got point D. D was -256, -256. So now I can say U equals, because I already named it U, so I don't want to let it name it automatically. So if I wonder if I can do this. Yeah, it doesn't have to be uppercase. And so now I can say, as I did before, vector from C to D. And then again, that verifies that I didn't screw it up because that's exactly what we got, -6, 7, -2. So I think I'll erase this, but just for the heck of it, if I said capital E is the point, -6, 7, -2. In other words, I already did the subtraction. Then could I say vector and then just list the point E, and then it says it'll do it? Oh yeah, good. Okay, that's how you do that. But again, notice where it put it. It put it, well, where it wanted to put it. But first, but do you agree that, and notice it gave it a name, like I never gave it a name. It said, oh, I guess I'll call this W. So it's like picking lowercase letters in the end of the alphabet for names of vectors. So do you agree that vector W and vector U are the same vector? Because vectors can move. So they're actually the same vector. So again, it's kind of cool to, I don't know, drag them around and just sort of see, oh yeah, look, they are parallel. They're the same exact vector. If I look at them from the side, yep, look, they're parallel. So that's kind of cool. Whereas AB is definitely not. So, okay, that was fun. Get rid of that. Except for I didn't really want to get rid of that. Is there an undo command? Yes, good, there is. So now I'm curious, since we think we know the answer to U plus V, I'm wondering if I can get away with just typing U plus V here. And again, I actually don't know the answer to that. I'm guessing the answer is yes. If it doesn't work, I'm actually going to be kind of disappointed because I don't know what to do. So, hey, that's kind of cool because isn't that what we got? -2, 2, 8. So there's the sum of those two vectors. Now, interestingly, if I hit enter, notice it also gave that a new name because it's now a brand new vector. So it called it W. It stole the letter W that I just used a second ago. And so there's this new vector W. And I like that it labels it because now that I look up here at my sheet, I realize, you know, oh, cool, there's W right there. So awesome. That should be a little unsatisfying to you, though. Why do I say that? Again, I'm asking you to read my mind here, but why do I say that? Why is that a little unsatisfying?
Is it because like when you see vector W, you don't see it like as a triangle, like the head to tail connection?
Exactly. If I'm thinking U plus V, I'd like to move U so that its tail is at the head of B. In other words, C moves to B, and then I can actually show that this vector indeed completes the triangle, like Alyssa just said. And so in a sense, I know I got this right mathematically, but I'm not really visually seeing it. And so now the question is there some way I could move those? Can I move those vectors to kind of be where I want them to be? Can I get them in the right locations? Is there some way I could kind of visually see this a little more satisfying? Because my initial vectors U and V are, kind of not in the right location. If you're going to say you're going to add them, then the picture is no longer correct. So I would be really cool if I could grab this vector somehow and move it. And I don't know if I can do that. If I do, does it make sense? Point C right now is labeled as 4, -2, 8. So if I grab that, and it looks like I can, and I drag it somewhere else, is it going to that point right now? I can't really tell. Do you see how it doesn't want to go there? Not only that, but as I'm dragging it, it's totally screwing up C. It's screwing up the vector because I need to grab the whole vector and have it move parallel. Does that make sense? So that's not working very good. So maybe there's some easy way to do that, some move command or, whatever. I'm going to do this a little more manually though, because realistically, mathematically, what do I need to do to get that vector to stay U, -6, 7, -2? I need it to stay that, but I really want it to go from B to, well, some point I don't know where it is. Does that make sense? I don't really know where that is. So it's almost like I want to go back here and type over the top of the C and put a B there, but then I got to have some new point that I don't know exactly where that is. Just going to give you a second to think about that. I'd rather make this manually happen. Perhaps there's some command over here, like I saw move, I think someplace. maybe there's some kind of command I could sort of cheat, something of that nature. But I'd rather just kind of try to do this mathematically. So my first thought, and again, that's really all it is a thought, is could I come back and just make like a brand new vector? Except call it, you know, a vector from B. It's kind of like I already have all the ingredients here. It's like I kind of want to start at B, but then I want to go through U. Does that make sense? I want to start at B, but then I want to go U. I don't want to start at 0 like the U plus V did. I want to start at B, but then just do U after that. Does that make sense? So is there some way I could say vector from B through U? That's my first thought. I actually don't know the answer to that, so I'm going to try it. Vector, can I say from B and then say comma U? Notice it says, no, you can't. And it sort of makes sense because it said point, start point, end point. Well, this wasn't -6, 7, -2. Again, is not a point. It's a vector. That's why we're doing today. So I sort of see why it didn't do that, because it wanted a point and U is not a point. And so, bummer. I was hoping to cheat. Anybody have any good ideas?
I'm looking up like a GeoGebra manual right now, trying to find it.
Well, I mean, there's two answers to this. One of them is, can we just do this mathematically manually? And the second one is, can I get GeoGebra to do this in some cool kind of way? And ultimately, I want to know both answers. So yeah, if you figure that out, Raymond, tell us. What could I do to get it done manually, though? Because I want you to stare at this for a second. Take a look at these three sort of components. I have C, so vector U goes from C to D. And we said that vector U is found by just actually subtracting, like -2 minus 4 is -6, 5 minus -2 is 7. And so is there some way I could kind of figure out some new point? Like I want my new vector to go from B to some new point, like some point that I haven't figured out yet. I'm going to call it E. The question is, could you tell me what the coordinates of that are based on the math? Like, if it goes from B to E, and when you subtract, you get -6, 7, -2, can't we just figure out what point E is?
Couldn't you just take from B and add the magnitude of the vector you want? And then that'll set it to the new point.
So is it add, is Thomas's thought. In other words, B was 3. So the x coordinate of B was 3. And then I want to go in the x direction -6. So you're saying if I take 3 and I add -6 to it, I get -3. So there's my x coordinate. And then if I take -2 and add 7 to it, I get 5. So there's my y coordinate. If I take 6 and I add -2 to it, I get 4. So I have your educated guess correct?
Yeah, I guess.
So now that I sort of have manually established this new point, then I can just say I need a vector from B to E. Notice I'm not giving it a name. I'm just going to see what name it gives me. So apparently vector doesn't like anything unless it's got kind of a point represented. when I say enter, oh, notice it gave it a lowercase name. I actually thought it was going to stay in the upper end of the alphabet. So I'm learning all kinds of stuff today. Notice Thomas is exactly right, because notice it gave me the right answer, -6, 7, -2. It makes sense, doesn't it? Because to get this vector, didn't we go from C to D? Didn't we go D minus C to get this answer? So wouldn't it make sense then to go C plus vector to get D? Isn't that the opposite of subtract, add? Good for you, Thomas. So there, I just manually moved it. And so that's cool. And notice it's also kind of cool that you can go back and sort of turn off, like just to take the confusion down, you can kind of turn off some of the points. You don't have to erase them. You can just quiet them down a little bit. So now the question is if I move this vector over here into this location, will it actually go head to tail? And notice this is actually really easy to figure out because I can just say, well, don't I have point A and point E now? So if I just draw a vector from A to E and check to see if it's the same as the W vector, because the W vector we're told is -2, 2, 8. And so if I go from A to E and it's also -2, 2, 8, then wouldn't that kind of show that I got it right? Tracking? Vector from A to E, enter, gave it a new letter name. Oh, look at that, same exact answer. Again, it's kind of cool to go back and turn this one off. And so that's what I really just did. And notice that kind of verifies that everything worked. And so that's kind of cool. So apparently it's actually not, it's not kind of letters at the end of the alphabet and letters at the beginning. It's like lowercase is reserved for vectors and uppercase is reserved for points. I actually don't know the answer to this. I'm going to check right now. If I go say lowercase c equals 2, 3, 4. Yeah, notice it actually thinks that's a vector. So although it didn't say vector, that's kind of interesting, but notice it showed it as a vector. So I typed lowercase c, and that's like how you tell it you want a vector. So that's not an ordered pair because I don't have the ability to put the little bar over the top of it. Does that make sense? So that's kind of cool. I didn't know that. Now, why is what I just showed you so powerful? Well, in the context of what I just showed you, it's not powerful at all. It's totally irrelevant. But what I'd like to do is take this to kind of a new level now. Let me see if we can get to a spot where I can see it. Vector A, B. For some reason, there's no label on that one. I don't see a label on vector A, B. It should be a V there somewhere, and I don't see the V. I'm not sure why. Let's see, I sure would love to see all of that. Is there any way to see all of that? I don't think there is. Now, as I said, if you just see this as like, you know, vectors being drawn head to tail, you're missing the bigger picture. So what's the bigger picture here? Well, the bigger picture is you've got one sort of, let's say, member on a bridge, like a piece of steel. And we're interested in this point right here. That's a joint on the bridge. And so there's this connection over here that's kind of pulling off in this direction. And so it's pulling in that direction. Well, if that's the only force on it, that's not good. The bridge is going to fall down because it's got this force on it. But there's also another force pulling on it. And ultimately, this BE vector would actually be written over here. Like it would actually be drawn from A. You got one pulling this way, you got one pulling this way. But now we got two forces pulling on it. This is kind of what I showed you yesterday. So the question is, well, where's it going to go now? Well, if I move this vector from down here up to here and draw it head to tail, and then I draw this vector that goes from the initial tail to the final head, then that's the direction this thing's actually going to go. Maybe a better example that I'm about to use with you is like, let's say an airplane. And so here's the airplane trying to fly in this direction. at say 40 miles per hour. That planes fly faster than that, but it's flying in this direction 40 miles per hour. And so, you know, in the absence of wind, it's just going to fly in that direction 40 miles an hour. Great. So the 40 would be the length of the vector. And the ordered pairs that I gave it kind of help you with the orientation. What direction is it flying? And so that's the power of vectors. It's how fast are you flying and in what direction? You have to know both or you don't really understand what's happening there. But unfortunately, there's wind blowing. And the plane is flying in 3D and the wind is blowing in 3D. So these vectors could point anywhere. And so although the airplane's nose is aiming at B, it's actually flying sideways and it's actually going clear over here. Notice this is a good example, or at least a very pronounced example, because the wind is super strong. Based on what I see right here, it looks like if the airplane was flying 40, the wind is 30. And so it's blowing it way off course. And so if you're a pilot, you don't just go, okay, bummer, I guess we're going to land in Guam instead. You say, oh, well, if that's going to happen, then I guess I'm going to have to aim way over here somewhere. Does that make sense? I'm going to aim way over here and then the wind will blow me to B because that's where I want to go anyway. Right. And so that's what head to tail really comes down to. As a simple example, it's two forces acting on something and then where is it going to go as a result of that? So I want to show you something kind of like what we just did, except practical and powerful, again, to just grow your intuition. So let me share my regular screen. So there's no assignment today. This is not something I'm going to test you on. I'm going to show you some cool stuff that's deeper than what you understand right now. So if a plane is flying in 3D, so here's the weird thing. Like if you're usually in the case of bearings, if I say, well, tomorrow I'm actually going to fly to Idaho, for instance, and I know Idaho is like, well, north and a little bit toward the east. And that's all you have to know to fly an airplane because I'm on the ground now and I'm going to get up in the air, but then I'm going to be back on the ground again. So does it make sense? All I really need to know is I just need to turn from north, say 30 degrees, like from a map. I could measure that with a protractor and then just take off at that angle. And then eventually I'll see, oh, like, look, there's Idaho, cool. And then I could land there. But in the end, the plane is actually taking off at a vertical angle. So, you know, let's think of it as like a rocket or something like that. But to make it a little more interesting, let's see. Let's do this. Number one, so a real example. One, airplane. We will say it flies at 220 miles per hour. So there's the length of its vector. Does that make sense? Now you just need to know where to point it. So again, what's so cool about this is miles per hour is not a length. That doesn't say feet. So vectors can be pounds, they can be miles per hour, they can be sort of any, well, mathematicians would call them scalar. That's a scalar quantity or a numerical quantity. So that's a numerical, just a number. And so, but we need to make a vector out of it so that we can say what direction it's flying. So what direction is it flying? Well, now I can't say let's fly to the point 167. Does it make sense? That doesn't make any sense like in the real world to say you're gonna, it's like where's 00? Is it the airport you're at? And what does it even mean to fly to the point 193? You know, it's like, oh, I'm gonna take off in that direction. That's really convenient on X, Y, Z axis like we just did, but that's not realistic if you're an airplane. So let me tell you how that works. Well, with some, there is a transverse angle. Again, you don't need to know this for a test or anything. This is just cool. It's cool to understand. A transverse angle theta, which is actually in the XY plane. What's wrong with me? A transverse angle theta that's in the XY plane. And that's as you're used to. In other words, you first start out, you just think of it on the ground. And so I'm sitting in my chair right now and I'm thinking, okay, there's 0. And 0 for us is, remember, 3 o'clock. It's like over there, you know, to the right on XY plane. So you start at positive X, and then you turn counterclockwise, however many degrees that you say. So that's nothing new. You already know that. That's why I called it theta, because you're used to seeing theta as an angle. So I sort of sit here, I'm in the airport and I'm in my plane. I'm about ready to take off or rocket or something. And I say, okay, what direction shall we turn in the XY plane? Notice I'm level. It's like, okay, let's fly that way. All right, let's fly this way. Now, what's the second thing I got to do? I got to decide, well, what direction from there? Am I going to fly, you know, up at 30 degrees, or am I going to fly pretty low to the ground? Am I going to shoot straight up in the air? That's the second angle that you've got to know, which is called the azimuth. Azimuth. Anybody know what that Greek letter is? You are advanced math students. You should begin knowing your Greek letters.
Is that phi?
Yeah, phi or phi, P-H-I. If you go to a four-year college and you join a frat or a sorority, you might be a Gamma Phi Beta. Not sure how the alphabet, the Greek alphabet, got into that system, but somehow it did. That is effectively the Z. It tells you where you are, not in the Z plane, but in the Z axis. And oddly, it's measured from vertical. In other words, what I would think if I was an airplane is like, I'm going to turn this way, and then I'll measure 30 degrees from the ground. In other words, up from level 30. But if you say 30 in this language, you actually start from straight up and down like a rocket and you come down 30. Does that make sense? And then you take off. And so does it make sense? It only takes two angles to say what direction to go. That's kind of cool. And you know, Ben probably remembers this, but we struggled mightily in statics trying to picture these kinds of things, because this was a part of it. Like, what direction is this force actually going? In 3D, it's just so hard to picture. And so there's two ways of measuring points. One of them is an XYZ axis, but the other one is a couple of angles. And so let's say for our purposes that the theta angle is 214 degrees. And let's take off kind of like a plane would do, which is 82 degrees. And so let me draw a picture of that. Let me just draw a rough picture of that. And so our problem is, you now know everything you need to make a vector out of this. Does that make sense? You know what direction it goes, although that's a confusing set of directions. But you also know the length of the line. And so I want to know, could you stick this into GeoGebra? But let me just make sure you understand this if I draw a picture of what direction this is actually saying. So as per usual, there's X and there's Y. And here's Z. So your spatial awareness here should be, you know, making smoke come out of your ears. So you stay first in the XY plane and turn 214 degrees. Can you do that? Can you picture where I'm about to draw this? Can you see this 3D? There's the negative side of the X-axis. There's the negative side of the Z-axis. And so I'm going to turn, well, from positive X. Remember, this is actually 0 over here. That's 0 degrees, isn't it? You're just not used to seeing it there, but isn't that where 0 has always been? So I'm first looking at the plane, the XY plane, and I'm saying, let's turn, well, isn't it 90 degrees to there and 90 more degrees to there? So I'm at 180 now. And so then I've got to turn, what is that? Another 34 degrees? Is that right? 34? Yeah. Another 34 degrees. So I guess I would be kind of like there. So whoop, there's theta, 214 degrees. So now I know what direction I'm going to travel horizontally. And now it's time to kind of come down from the top. And again, my two-dimensional drawing here is going to make this very hard to picture. But basically now I'm turning from straight up, this positive z value, I'm turning downwards, phi, 82 degrees. So I'm basically lifting off the ground 8 degrees, right? 82 plus 8 is 90. So I'm basically tipping up 8 and then taking off from there. So the question is, how are you supposed to and in a sense, I guess my drawing is a little bit is not, I'm actually going to improve my drawing a little bit while you're cogitating on that. Because I can't really draw because right now that blue vector is actually on flat ground. Does that make sense? And now I got to lift it up in the air a little bit. So I think I'm actually going to draw it lifted up in the air a little bit. So it's like a brand new vector. So this is our, we'll call this airplane, vector A for airplane. So there's A now, and I had to turn down. Because if I went down to the blue one, does it make sense it'd actually be 90 degrees? Does it make sense it's 90 down to the blue vector? So I can't really draw that to the same exact vector. That doesn't really make sense. So I'm actually turning down phi right there, 82 degrees. So
Real quick, where did we get the 82 for the fee?
I just made it up. I mean, if you're going to fly the plane, you get to fly whatever direction you want, right? So that's me just telling you, what direction shall we fly? We're at the airport. Where you want to go? So I just made those up. Am I answering your question? I didn't calculate that. No calculations have been made yet.
Yeah, I just wanted to make sure it wasn't something we'd gotten from the circle.
So do you agree this is the magnitude of your vector? And this is, if you will, a creative way to give the direction. It's an annoying way, by the way. Like you don't want to be given the direction like this. You want to be given it as an XYZ. It'd be way nicer just to have XYZ for this. So what I really need now is I need something that's like, okay, great, nice work. Vector A is equal to number. That's what I need. Like it's pretty easy to do your math if you write it as a vector, but wow, how do I get this? How do I make a vector out of A? I don't want to let you off the hook too quickly here, so I want you to think about that a little bit. Let's see if you can figure that out yourself. How am I going to get an X? Because a vector is an X, Y, and a Z coordinate. You got to give me an X, Y, Z coordinate for that red vector. If you can't do that, then you can't do this. That's the beauty of what vectors are. If you break them into X, Y, Z components, because I'm going to add wind to this in a second, we're going to have the airplane try to fly along the red vector, but then wind's going to come in and blow it off course. So we're going to need to add the red vector to the wind vector to see where the plane actually flies. If you can't write this as an XYZ, then you can't do the beautiful, basic, easy math and just add them together. That's why vectors are so powerful. If I gave you the same 3 types of numbers, like a mile per hour for wind and a transverse and azimuth angle for wind, and then I said, okay, now where's the plane actually going to fly? You can't do it. Like you have to convert these to X, Y's, and Z's. I'm giving you some hints here. The question is, how good is your spatial awareness? Do you see these two right triangles? Do you see those as right triangles that I just drew in there? The blue vector was drawn first, and then the red vector is straight above it. It's right above the blue one, actually. You basically lifted it up, if you will, 8 degrees. So you actually have a couple of right triangles right here. I'm wondering if you agree and understand that this is your X. Is that right? Is that X? Yes. And this is your Y, and this is your Z. That's what I need to know. I need to know those links right there, don't I? Notice X is negative, Y is negative, but Z is positive. How are you going to get those? Because I don't see that I know anything. We do know one thing. What do we know? We know the length of that red vector is 220. That's what we know. Armed with that, we can work our way through those right triangles and find every length we need. See if you can do it. It's just basic trig if you can actually visualize it, see it. In the red right triangle, you know 8 degrees, Z is the opposite, 220 is the hypotenuse. You should know that, oh, that's a sine problem. The sine of 8 degrees is opposite over hypotenuse. Make sure you're in degree mode because we're usually in radian mode in this class. I am in radian mode. Quit mode. Degree mode. So I'm taking 8 times, or I'm taking 220 times the sine of 8. I got 30.62. So Z is approximately 30.62. I think I better just call it 30.6. Don't want to have large numbers. And notice I can calculate, I guess I'm going to come down here and call this for no good reason W. I can also calculate W by taking the cosine of 8. which is 217.9. But I don't need to know W, but notice W, which is the leg of the red triangle, becomes the hypotenuse of now the blue triangle. And now I can get X and Y. So I can say that since 34 is across from Y, I can say that'd be the sine of 34 equals opposite, which is Y over W. So I have 217.85897 still in my calculator, so I might as well just say times the sine of 34 so that it's still accurate. And I get Y is 121.8. And finally, the cosine of 34 degrees would be adjacent over hypotenuse. So again, to get it exactly right, I'm going to get that 217 number back in my calculator exactly correct, and then say times the cosine of 34, and I get 180.6 for X. Now, I wanted you to see how simple this is, but you may understand that I could have used the angle. Remember, the actual angle theta was, what was it, 214? What's wrong with this statement right here? If I say, sweet, I know I have vector A. I found it. X, Y, Z. What's wrong with that? If you took off in that direction, where would you fly?
You've got need to take into account the negatives because
Negative.
you're actually going in the negative X and negative Y direction.
Negative X, negative Y. So based on the way I did this, because I used 34 degrees, I've got to apply the negatives myself. If you had taken the sine and cosine of 214, not 34, then the 121 and the 180 would have came out negative automatically, right? That's why you studied trigonometry in this class. So we could formalize this and kind of make it go faster and so forth. If this was a navigation course for like Navy pilots or whatever, it would be easier to work with 214 and that would happen automatically. But I just wanted to make sure you see, this is just so Katova. But I have to assign these negatives myself. Otherwise, I'm going to get this wrong. You understand what those are? What are those? Are those lengths? What are those? Nobody? Remember what 220 was? It was miles per hour. Those are all miles per hour. As a matter of fact, what am I going to get if I ask for this? This is something I want to be able to ask for in a test and you know what to do. What does that mean to do?
Magnitude.
Magnitude, which is square this, square this, square this, and add them together and take the square root. You should already know what I'm going to get for this without even typing it in. But I'm going to type it in. The reason I'm going to type it in is because I know what this is supposed to produce, and I'm going to use this to check my work. I got 219.97. That's good news because I should have got 220, and I didn't get 220, but I got 219.97 because I rounded, and so of course I didn't get 220. But the red vector's length is 220, and the unit of that is miles per hour. So that means all these units are miles per hour as well. So do you see what we just did? We broke the plane's speed, which really was a hypotenuse, We broke it into its X, Y, Z components. So the powerful thing about this is, since X, I wrote that wrong. I see now. I put Y there, but that was actually X, wasn't it? This was negative X. What this means is, let's say there was some town, over here, like right along that X axis, and you flew in that direction. The reality is you're flying 220 miles per hour, but does it make sense all 220 of it is not devoted to getting to this town right here? How much of it is devoted to getting to that town? 180.6. 180.6 of your miles per hour is going toward that town. So if it's a question of like, well, when are you going to be, when are you going to fly over that town, or where are you going to fly, and when are you going to be equal with that town? Well, you'd want to do your math off 180, not off 220. Or if these were forces, if you're pulling 220 pounds and you're pulling in that red direction, well, how much of it is actually going along X? It's going to be a very important concept when we get to dot products, not tomorrow, but Monday. And so only 180 of those pounds are actually doing any work in the X direction. Does that make sense? So yeah, you're pulling at 220, but very little of it is going in X. Notice how little of it's going in Y. If this was a force of pounds, only 30 pounds are actually being pulled up. It's not being lifted very hard. Again, why is that? Well, you're flying mostly level, so you're not climbing very fast. You're only climbing off the ground at 30 miles per hour. So if you will, if all you cared about was vertical, how fast am I rising? 220, I'm flying 220. No one cares. What you're flying is 30. You see what I'm saying? That's the power of this. You're breaking it into its components, and that makes it totally easy for it to interact with other forces that are acting on it. So, of course, 220. That means I didn't screw any of this up. That's amazing. That's really cool. So we've got to kind of mark this out. We're very stoked. We now understand the airplane's flight as a vector. So now you are on your own for the wind. Secondly, 1 airplane, 2 wind. Let's give it a speed. Now, I could give it a small speed like 10 miles per hour, but I want it to be significant enough to really blow the airplane off course. So I'm going to make it kind of an unrealistically large wind. Let's make it like, what did I decide ahead of time? That seems kind of small. Let's make it like 52 miles an hour. That's actually not terrible. Planes actually fly in that. But notice that's like 1/4 of the airplane. That's a pretty significant contribution it's going to make to the airplane. Now, listen to this carefully. Is that going to blow the airplane off course? I want an answer to that.
Yes.
The answer is maybe.
Depends on where
Not
it's blowing.
automatically yes. What's the special case where it wouldn't be yes?
If you're flying with the wind, I guess.
Yeah. Does it make sense if the wind was going exactly the same direction, it actually wouldn't blow you off course. It would actually just make you get there 50 miles an hour faster. But it could also be right in your face. Perfectly in your face, you're still going to go the same course, but you're now going to be going 50 miles an hour slower. So realistically, the answer is yes, because it's probably not exactly behind or in front of you. But if I give it some different direction, does it make sense if it's a little behind you, then you'll have a tailwind, which will speed you up, but will you be going 50 miles an hour faster? No, because it's probably at a weird angle. Does that make sense? So the question is, how's this going to blow us off course? What's the best angle I could pick if I wanted it to just totally blow us off course? What's its path relative to the airplane's path if I want to really use that 52 to blow me off course?
You can make it perpendicular, and that would.
That's
blow it off
exactly
course.
right. Perpendicular to it. Now, if I made it perpendicular, it would not change my speed one bit, because it's entirely pushing me off course. It wouldn't change my speed. I'd be still going 220, but all 52 miles per hour would be directed and making me go way the heck off course. Does it make sense? It could be slightly off course and, mostly speeding me up. So that's what's kind of fun about this is, it's kind of hard. It depends where the wind's blowing. And so that's why a vector includes not just the magnitude, but also the direction. And so let's just make up again, kind of like before. I won't write all of the azimuth junk out again. I'll just say theta is, well, we picked 214 for the other one. So let's pick 98. Let's pick 98 for theta. And phi coming down from vertical, let's make that 36. That seems very different, if you will, than the airplane. That's all I was really trying to do here, just make it a lot different from the airplane. So the question is the same. What is vector W? We'll call it vector W. So we get air for airplane, W for wind. If I'm successful in writing the wind in miles per hour as a vector, then it'll be total, work is over. This is the hard part. If I add them, then I know exactly where the plane's going to go. So if I can survive this, cool. Just for your knowledge, try to draw the right triangles like I did last time, just to make it easy. You can see why a formula would be better. Like I'd rather work with 98 and 36, just use those angles. I'd rather make this formulaic, and so I could just use those. And that is the best way to do this, but that makes it look magical. But you may notice last time I didn't use either of those angles. We changed them. We used the opposite of them, if you will. if you're not naturally gifted, which I would assume about 75% of you would not be at visualizing all of this, you can steal my picture now if you need to. Check your work if you want, or check mine, because I might have made a mistake. I did make one mistake on purpose. Make sure you catch it. Where the right triangle goes in 3D is very hard to visualize. Right angle in the right triangle, I should say.
Is that 4.3 supposed to be negative?
Exactly. That's the mistake I made. My numbers are right, but you got to see that X is negative. Notice this time the Y is actually positive.
Yeah, I used 36 and 8. Did I miscopy?
36, the azimuth angle is the angle down from the top. In other words, it's from vertical. So before that angle was 82 degrees, 82 degrees from the top down. Well, that left us 8 degrees from the bottom up. So because it was 36, I said, oh, okay, well, if that's 36 down, so this angle right here is 36, then that angle right up there would have to be 54. I just thought that was an easier place to draw the triangle. Now, there's nothing wrong with drawing the right triangle up here and using 36. That's fine. You can do that. But it's a
Yeah.
different triangle. So,
Yeah, I drew mine like yours, but I had 36 in there instead of 54. That's why.
yeah, that's not true. And
I
the
did the same thing.
automation of this process, again, I don't want you to know this. It's just kind of cool. You might need to know this in some other class. You'll need to know it in my dynamics class or statics class. It's easier to work with theta and phi just as they are. But I think it's easier to see the airplane doing what it's doing. Like you turn 8 degrees from Y and then you angle yourself up 54 and then you take off and fly. It's easier to see the right triangles if I draw them like that. But yeah, you don't have to draw the right triangles the way I drew them. So that's the hard work. The vector part's totally easy. Now I just say, great, we got airplane vector plus wind vector. All I gotta do is add them. And notice it's kind of cool to see that some of them are working together. Like the X's were both working together negatively. Notice because of the direction though, the wind didn't make much of a difference in the X direction. So negative 184.9. I'm going to write them vertically just for the fun of it. No, actually, I'm going to write it as a I's and J's just because we're practicing, right? The Y values worked against each other, but the airplane negative 121.8 was sort of much more powerful than the wind's contribution of 30.3. So it only left 91.5 in the Y direction, but again, negatively. And notice the wind was blowing up and the airplane was going up. And so the wind was actually lifting it up in the air quite a bit more than, it would have on its own. And so the wind actually lifted it more than the airplane did because the wind was angled so high. Does that make sense? And so, whoa, that's pretty big, 72.7, which I could write as 72.7 K. And so that's the direction the airplane's going to fly. That's pretty cool. Now, the interesting thing, though, and we're going to stop here just because we're out of time, but the interesting thing about this is that's not very useful, what I just wrote. You actually would want to convert it back to angles and also to the magnitude. And notice you don't have to work that hard for the magnitude because you can actually just do Pythagorean theorem on those numbers. And of course, that's really interesting because it's going to tell us how fast we're flying. So I do want to calc that really quick. What is the magnitude of those two vectors added together? Square root of, and just leave the negatives out, 184.9 squared plus 91.5 squared plus 72.7 squared. I got 218.7. What does that tell you about, what does that tell you relative to the original speed of the plane?
It's less than 220, right?
Yeah, it's a little, and notice it's very slightly less than 220. So what does that tell you about where the wind must be? Because it's hard for me to picture this, right? Where
Probably
must the
head
wind
on.
be? Yeah, but not straight on, because it would have slowed me down 50 miles per hour and I'd be going like 170. It must be slightly in my face. You see what I'm saying? Because it really didn't slow me down much. This actually must be the case where it's mostly blowing me off course. Slightly in my face, but mostly blowing me off course. But of course, the other important answer to this is, what is in the real world? What are those two? Because it's like, great, that's awesome. You know how fast you're flying, but you're not going to land at the right location. Like, you got to know where this is actually sending you, right? So you can do something about it. I mean, that's the idea here. So by itself, that's not super helpful. And so, how do you get those back, if you will? How do you undo all of this and get your angles back again? I mean, that's kind of interesting from a actual pilot perspective. So it's 9:26. I want to graph this just because I want to visualize it. It's not very satisfying to me, so feel free to go. But I want to go back to GeoGebra and fly. I want to fly. So let's see. How do I do this? I'm going to try to use what I already have here. No, I'm not. I'm just going to get rid of all of it. So vector A, the airplane, and notice because we use what we learned today that I didn't know before is if we use vector, if we use A, it actually thinks this is a vector. So I'm typing in negative 180.6 and negative 121.8.
Not sharing your GeoGebra screen. You're still on.
Thank you. Thought I was sharing and I was failing to share. So negative 180.6 and negative 121.8 and positive 30.6. Notice, again, I'm just trying to visualize this. That doesn't look right. Does that look right to you? I'm totally confused by what I see there, but remember it's because it's 3D. And the other part is that's really long. In other words, I'm gonna have to sort of zoom way out to even see this. There we go. Does that look right to you? Like stare at that for a second. So notice positive X is red. So positive X right now is over here. So we turned 90 to here, 90 more to there, 180. And so this is a little past this. I can't really picture it unless I spin it around. And if I spin it around kind of the way our other one was, notice that's a lot more helpful. So like from the air, oh, okay, yeah. From the air, that looks right. And then from the ground, it's like, oh yeah, that's going 8 degrees up in the air. So, okay, that's awesome. Now notice I had the luxury, if you will, of thinking of that first, the origin of this is just being at 0, 0. But now I got to take off from this point up here and then go the rest of the way. So let's see if I can pull that off based on what we did earlier. So I'm going to call the point capital A. I'm just going to use the same exact points, 180.6. I'm just thinking out loud here. I'm thinking this is going to work. Negative 121.8 and 30.6. So I'm basically just putting a point at the end of that vector up there. Except for I went dyslexic on it. So now I'm going to take off from A and then fly in the direction of our wind vector, right? So let me see, do I have this right? Thomas's idea was I just need to add to that our wind vector. So I have this point here. And if I add that to our wind vector, what I'm not sure is it, yeah, I think that's right. So if I take negative 180 and I add negative 4.3 to it, I get negative 1. Actually, no, I can just type our answer, can't I? It's 184.9, isn't it? Negative 184.9 and negative 91.5. Is this right? And 72.7. I'm actually not sure this is right. I think it is. So then I can say vector from A to B. So that's what the wind was actually doing. Again, notice that looks very confusing because that's now measured from A, whereas it, in a sense, we would like to have drawn it as starting from the origin. So yeah, do you see that it was slightly a headwind? Do you see that now? It's slightly angled toward us. It's mostly blowing us off course, but do you see how that angle looks to be a little less than 90 just at a glance if I spin it correctly? And therefore it is slightly in our face, which is why it slowed us down here. So this is actually looking really good. And so the important thing, of course, is to say, well, then what's our actual direction of travel? Well, notice I can just say lowercase v, and I can just retype that vector, the sort of b vector, negative 184.9, so that I can actually see it. So this last vector I just typed is actually the course that you're going to take. And of course, the powerful thing here would be to calculate this angle right here. And let's think for a second, just because this is kind of cool. Would you be able to calculate that angle right there in this triangle in the air? Can you calculate that angle? Because that's the angle that's blowing us off course, right? That's the thing we really need to know, because we're trying to fly from the airport here at 000 to A. But unfortunately, thanks to the wind, we're actually flying toward B, right? So if I could know what that angle was right there, then I could just adjust my angle by that much and I'd be okay. Let's not do it because we're way out of time, but what would you have to do in this triangle to be able to find that angle right there? It's not a right triangle. How's your trig skills? Don't you know all three of these links right here? Can't we just know those? Since we know their vector components, could we find their magnitudes? We could find all three of those links. And if you know all three links, couldn't you use law of sines and law of cosines to find the angles? So then the main angle we want to know, as I said, is this one right here, because that's how far it's kind of blowing us off course. And notice it's blowing us, as we calculated, way higher. Like we're blowing way up in the air higher than we planned. So that's a problem. But it's also from the air blowing us, slightly off course this way as well. So this is very complicated in 3D. And in the end, that's the strength of vectors. The fact that you can actually get 3D problems right. If you tracked with what I showed you today, your intuition and use of GeoGebra has maybe gone up a bunch. And so I'm hoping that's the case. I learned a lot today. Seems like I already knew this, I'm sure, but it's like I was just playing with it, just like you, and seeing what worked. So if you're still here, ridiculously, if you want to go extra credit on this and like try to figure out the actual course you should fly, we thought, hey, let's take off at 220 miles an hour. That's fine. You're stuck with that. That's the plane's accelerator, if you will. But the main thing is we said, let's fly at 214 and 82. Boom, let's go. Great. Uh-oh, there's a wind. You actually need to change the 214 and the 82 to two totally different angles. You need to fly in a totally different direction so that the wind will actually blow you on course. Does that make sense? Watch this, because I'm having a brainstorm right now. And this will actually come into play tomorrow. Do you notice that if I actually took this vector BA right here and moved it down, so it went from A and I just moved it, but notice I turned the arrow the other way. In other words, the wind's blowing this way. What I've got to do is take that vector right there and move it over here so that it goes down this way. Because if I aim to this point down here, then does it make sense the wind's going to blow me back to this point over here? So I'm actually going to subtract those vectors in order to find the direction I need to go. That's kind of cool. Anyway, way over time, gotta shut up. You guys have a good weekend. I will see you on Monday.
Real quick, since Monday is Memorial Day, do we actually have class?
No, we don't. I'll see you on Tuesday.